Okay, Bismillah ar-Rahman ar-Rahim. So we started considering the radiation characteristics of opaque materials. From what we have covered so far in this chapter, there are some sort of like a key takeaway, something that you would recall and keep it in your mind from what we have covered. We have been into the introduction of uh, these properties, I mean, absorptance and the emissivity, as well as the reflectance of a surface. And we've been talking here at the beginning of what does it depend on? Does it depend only the wavelength? So you're having the absorptance as a certain wavelength, and anything at a certain wavelength, we call it monochromatic. And then the directional of dependence as well, if it depends on the direction, whether it is the polar angle theta or the azimuth angle. And actually the polar theta, because it changes, basically we refer to it always with in the term of cosine theta, so we consider it as if it's changing from 0 to 1, and it has been, instead of talking about theta as a replacement, the talk is about mu, and mu is cosine theta. So when we are talking about changes with respect to polar angle, we are always referring to as mu, instead of every time saying cosine theta and cosine theta. The definition of both the absorptance and the emissivity has been given as, for the absorptance, it's a fraction of the incident energy which is absorbed on the surface, be it at a certain wavelength, so it's called monochromatic. If it depends on the directions, then it's like directional monochromatic absorptance or absorptivity. When we come to the emissivity, then we are comparing how much energy leaving a surface compared to the amount of energy that could have left if it's a black body or a perfect emitter. If we are going to look for what we call the hemispherical absorptance, in which we are talking about the total absorptance for the whole wavelength and for all directions. So the integration here is over the wavelength, over the polar angle and the azimuth angle as well. And that applies for both, for the absorptance as well as for the emittance. We talked about which of them are considered as surface property. And then we moved into Kirchhoff law, which is saying that the absorptance and the emissivity are supposed to be equal to each other. And as I mentioned, there's a couple of proofs for that. One of them is given in the book as some sort of a thought proof. Then we talked about the reflectance. And for the reflectance, we have to do some sort of a classification of surfaces, whether they are specular surface, and this applies to very shiny surfaces, so that there's an incident of angle of incidence and angle of reflection, which are would be equal if in case of a specular reflectance, or diffuse reflectance, so that the energy which is falling on the surface is reflected in all directions in the hemisphere. The general or the actual case is somewhere in between. So this is one extreme and this is the other extreme. And that's normally happened when we consider talking about something like modeling. In a model, you make an assumption, and then how good this assumption it appears when you get your results at the end and you compare it with the actual case. So both of these have been working fine with shiny surfaces as well as with diffuse surfaces, which are either black or gray. The formal definition of, yes, go ahead, please.
Sorry for interruption.
No, there's no interruption. Go ahead. Yes.
Some student cannot log in, Doctor, here. I think they need your...
Yeah, so far I'm logging whatever I am seeing here. I don't see waiting room. Is Yusuf and Muhaish here with us? Yusuf?
Yes, I'm here, Doctor.
He requested admission and I granted the admission. It seems to me, or it appears to me that he is joining, but I'm not sure whether he did join or not. The message of joining is there for quite some time.
Yeah, I'm here, Doctor.
Okay, fine. So you could join then. Because for me, it's showing joining. That's why I was wondering. Otherwise, I think whoever requested to be admitted, he is. And Yeah, I think we'll try it after that to make the login in without asking for a waiting room so that you log in directly to the class. Then we talked about the formal definition of the reflectance or the reflectivity as well for the surface here, which is how much energy is reflected as a fraction of the energy incident on the surface. Remembering that in this chapter, what we are talking about is opaque surfaces. And by opaque surfaces, basically, we mean that we are not considering the transmissivity through the surface, which applies normally for glass. Glass is going to be considered separately in the next chapter, or the glazing. So basically, what we are interested in here is the issue of both of these two properties, the absorptance and the reflectivity. And this is why we are going exposed to this relation. And this relation is one of the important relations that, or it's a key relation for this chapter, that the value of the emissivity is equal to the absorptance according to the Kirchhoff law, and both of them are equal to 1 minus the reflectivity. In some cases, we cannot estimate the emissivity, we cannot estimate the absorptivity, but we can estimate the reflectivity. So knowing the reflectivity here is going to be enough for calculating the other properties. And this relation is general, so it can be applied for the monochromatic case for each wavelength. The summation of reflectivity and absorptivity, or reflectivity and emissivity, is equal to 1. So this is applicable for monochromatic case as well as for the whole spectrum over the range of the wavelengths that we have. When we are talking about the emittance, again, if we are looking for the formal definition and how it can be given for a certain wavelength, the amount of energy falling into the surface is given by the upper curve. Here we are talking about the emissivity. The upper curve is the black body radiation, whereas the actual radiation is given by the lower curve. So for a certain wavelength, the ratio A over B is a definition of the effectiveness. This is monochromatic effectiveness. You need it for the whole surface, integrate. And the same thing here applies for the absorptivity, that at a certain wavelength, the incident energy on the surface is given by the upper curve, whereas the fraction which is being absorbed is given by the lower curve, so that for any wavelength, the absorptivity is, or absorptance is basically the ratio C over D. This is the monochromatic absorptivity. You need the total absorptivity of the surface. What you need to do is to integrate again over lambda. Sorry. Alhamdulillah. Now, the additional issue that we also talked about earlier is that talking about the absorptivity is depending on how much energy is incident. And how much energy is incident is basically depending on what are the surrounding surfaces that are emitting energy as sources, so that the current surface is absorbing part of it. So to determine the value of alpha, we need information about the other surfaces, which is not the case when we are talking about the absorptivity or the absorptance, the emissivity or the emittance and the reflectivity. So for the absorptivity, because we are absorbing energy falling into the surface, we need to know what are the main issues, what are the main characteristics, more information about the sources that are emitting the energy. But epsilon, it depends on the surface temperature. Reflectivity is a property that we can determine, so which means that in many cases, it's easier to determine the reflectivity, the emissivity, and then we can use the Kirchhoff law to obtain the value of alpha. Again, the general expression for the summation for calculating the emittance or the absorptivity can be obtained if we know the value of the reflectivity. Once you know it, then alpha is 1 minus rho, or epsilon is 1 minus rho. And this is again, this is what you can see here by talking about integration, it doesn't have to be a functional integration as we used to have in the mathematics, but numerical integration is an option. And integration basically means summation. So we are summing the ratios that are below the curves from I equal to 0 up to I equal to, theoretically speaking, infinity. But basically, we don't need to go up to infinity. It's just the range of the solar energy radiation is our limit. And this fraction is the value of delta Fi. And we have seen that delta Fi is being given in tables either for black body radiation or for terrestrial radiation. One of them for the black body radiation can be found in chapter 3, whereas for the terrestrial radiation can be in chapter 2. So you can refer back to these increments and the corresponding wavelength or wavelength and temperature times temperature for the wavelength at which these values are being estimated. So as a generalization, in case of equal divisions of delta F or the fraction of the energy, then you can get a certain general expression that relates alpha to rho. And if you know information about the reflectivity, then definitely you can get the value of alpha. We will see that in an example. So the example here is talking about terrestrial solar spectrum, where basically the reflectivity here is being given as a function of the wavelength. So for that surface, the reflectivity starts from a small value for low short wavelength radiation. And remember, low short wavelength radiation is corresponding to high temperature radiation. So for high temperature radiation, the reflectivity is small. It keeps on increasing up to a certain value of the wavelength. Here the scale has changed, and the value of reflectivity increases a little bit and then is kept fixed or constant. So we're talking about a surface property that provides us with a profile of the change of the reflectivity with lambda. And what we need is to calculate the absorptance for terrestrial solar spectrum and emittance at a temperature of 177 centigrade, which is corresponding to 450 Kelvin of the surface with this profile of the monochromatic reflectivity or reflectance. What we need to do here, now we know what is the temperature in Kelvin, 450, and we have a table that will help us to obtain the required values, as you can see it here. The table is table 361. To remind you of the table basically is, I thought I brought, yeah, the table is shown here. This table is given as the value of the subtotal emissive power, but it's given from 0 to lambda t for these values of lambda t. It's divided here into sections from 0 up to 1. So the fraction from 0 up to 1. That's how the value of the delta F is being calculated, and the corresponding value of lambda t, where this fraction is being given. The figure here is a recalculation of another figure, 361A in your book, and in 361A, the distribution is slightly different. It is given in the form of, let me see if I can plot it here. It is basically given alpha t, lambda t, and the corresponding f from 0 to lambda t. And the values for this table are given here starting from 1000 onward up to a value of almost infinity. And the corresponding fraction is being given here. So if you remember that we used to do an example or solve an example for this case using this part of the table that I've just written by saying, for example, how much is the fraction of the solar energy is is incident in the visible range. Visible range, we know that lambda is equal to, or ranges between 0.38 to 0.78. So multiply that by the temperature of the sun, and temperature of the sun is 5,777. So we get lambda T1, we get the corresponding F, lambda T2, we get the corresponding F, and the difference between them is this kind or representation of this fraction, assuming that the solar energy is treated as a black body. And we had that example earlier. Now this figure is being replotted in a different way, where we are basically not sorting it with respect to lambda t, but it is sorted with respect to the fraction of the energy, and the corresponding lambda t is being given here. This is the one that we are looking at now. So we are looking for fraction of the energy at a certain wavelength, which is provided to us, and we know the temperature, so the value of lambda t is estimated here. And when we are looking back again into the example, what we are looking for, we're looking for basically absorptance and emittance. So we're looking for alpha and epsilon. But the information that we have in hand are basically information related to the reflectivity, rho. So we're going to calculate the reflectivity, and then we're going to apply the property relations, which is basically reflectivity plus absorptivity, or reflectivity plus emissivity is equal to 1, and then we can calculate alpha as well as epsilon. Now, to do that, we increment the values that we have in the table. We don't have, the table has, for example, large number of rows. We don't have to follow all of that number. But what we can do, we can take it as fractions, for example. And this is what we're doing here. We are taking it as an increment of 0.2. So first, we are going for an increment from 0 to 0.2, from 0.2 to 0.4, 0.4 to 0.6, 0.6 to 0.8, 0.8 to 1. The table here is doing it in an increment of 0.1, but we don't need 0.05. We don't need to do that. Otherwise, the calculations will be too much. So what we are going to do, we are going to combine from 0.05 to 0.2, and then from 0.2 to 0.4. Yes.
Sorry for interrupting. Some guys are still trying to join and they can't.
This is weird. I'm not seeing. Let me try to see if I can.
It's about Dr. 8 people.
Oh, so let me see again if I can do something about that. It's strange that I'm not seeing him here in my in front of me. So yeah, this is strange. I cannot see them all. Just excuse me. I'll just have to stop it and restart it again. Maybe it's an issue with the computer itself or the software. Yes, now I could see the rest. So I believe everyone is here now. Sorry, I mean, I did not, the system did not show me that there is a request for entering the room. So as I mentioned a while ago, what I'm going to do is for the next meetings, I'll try to make it without a waiting room so that you just log in right away. We have been considering an example for the calculations of the absorptivity, which is a direct application to what we have talked about in terms of calculation of the properties. So the example is about calculations of absorptance for terrestrial solar spectrum and emittance at a temperature of 177 centigrade, which is 450 Kelvin, of a surface which has a monochromatic reflectance given by the figure. So here we are going to make use of the information provided, which is about the reflectance. And we know that, for example, that the emissivity or the absorptivity is basically equal to 1 minus rho. This is applicable on a monochromatic range, or it's given for the total range of the wavelength. The same thing applies for the emissivity, as the emissivity is equal to the absorptance based on Kirchhoff law. So what we are going to do here is we are going to look at a figure, which is a table, sorry, which is providing us with the increment of the energy fraction with the corresponding value of lambda t. This figure is obtained from figure 361, in which this fraction of the energies is being given and the corresponding product of lambda into T is being given. The temperature is known for us, it's 450. So for this fraction of the energy, we could have taken this table and did everything exactly the same. So what we need to do for this fraction of the energy, the corresponding lambda T is 1880, from which we can calculate the value of the monochromatic, for example, reflectance based on this wavelength. So what we do, once we calculate the value of lambda T, or we will get the value from lambda T, we divide it by the temperature, we get the value of lambda, and for the corresponding lambda, we get to the figure and calculate the value of rho. And we do that, we sum it all. Integration is a summation, so we sum it all, and then we see what's the representative value of rho. Or we don't have to do it for every line of that curve, but we can combine them. For example, we're going to combine them in fractions, or going from, instead of saying from 0 to 0.05, we're going to combine this all together in one batch, and these together in another batch, and so on. So to do that, we need to determine the value of lambda T in the midpoint. And the midpoint here, if I'm going from 0.05 to 20, is 10. From 0 to 20, the average value is 10. So we're going to take this one and the corresponding value of lambda T. And then going from 2 to 4, the average value is 3.3. So we're going to consider this one and the corresponding value of lambda T. Then from 0.4 to 0.6, the average value is going to be 0.5. So we're going to consider this and this. So we're going through fractions, as you can see it here. And these fractions are what's given here. From 0 to 0.2, the middle value is 0.1. And what's corresponding to 0.1 is 2,200. Then from 2.4 to from 0.2 to 0.4, the average value or the mean value is 0.3, and corresponding to the 0.33120 is the value of lambda T. So 3120, and we are doing it here. From 4 to 6, 0.5 is the mean value. We get the corresponding lambda T. From 0.6 to 0.8, the mean value is 0.7, so we take the 5590 from here, which is this. And lately, or at last, from 0.8 to 1, the mean value is 0.9, and for a 0.9, the lambda T or corresponding lambda T is 9380. So this is basically what we have done here. So we have like shortened the whole values that we have here in the table into only 5 increments. And these are the increments. This is optional. You can make it like 10 increments if like. So it becomes from 0 to 0.1, from 0.1 to 0.2, 0.2 to 0.3, and so on. What we did after that, this value is obtained from the table, and this is a representation of lambda into T. We know the temperature is 470 Kelvin. So divide this value by 470, we divide lambda T by the temperature, so we get the corresponding value of lambda. This is lambda in the mid-range that we selected, which is from 0 to 0.2. So these are the values of lambda. We have 1, 2, 3, 4, 5 of lambda. We take these values in the figure that we are provided. The first lambda is 4.89. So at 4.89, somewhere here, we're going to get the corresponding value of rho. And then the second value, 6.93. For 6.93, we get the corresponding value of rho, and so on. So for each one of them, we are getting the corresponding value of rho. At the end, what we need to do, make a summation of all these values of rho that we can see here, and we divide it by the number of increments. From here, we can get a representation of what is the value of epsilon as we are getting it here. I said it's optional, so we have selected 5 increments. Suppose that you have selected 10 increments. So what you are going to do, you are going to divide this as from 0 to 0.1, from 0.1 to 0.2, from 0.2 to 0.3, and so on. If you are doing it from 0 to 0.1, then you are going to take the corresponding value here, 1880. From 0.1 to 0.2, the corresponding value would be this. But in this case, you are going to take 10 increments here. And once you do that, again, you are going to divide each one of them by the temperature, which is 470. You get the corresponding value of lambda, and then you can get the corresponding value from the figure for rho for each one of them. And then you are going to make the summation as we are doing it here. The value that you are going to get here, if you take 10 increments, will be divided by 10, the number of increments, and then you can calculate the value of epsilon. If you do that with 10 increments, you can find the value is equal to 0.01. So here we are talking about a certain range of accuracy that it depends on your application. You may or may not accept it. So that depends on the practical application you are in. When you do that, you are going to calculate what is the amount of energy leaving the surface totally. And this amount of energy, for example, in kilowatts or megawatts, how does it differ? By going more accurately and taking 5 increments or 10 increments, or maybe take the whole range that you have here. Maybe you can take them all as like 20 increments, as you can see it here, and then do the summation and see accurately what would be the value of epsilon for this case. This is another example. In this example, we need to do what we did earlier. Earlier, we have done it for a black body case. I mean, we're looking for our reference was a black body. In this case that you see here, we need to calculate the absorptance for terrestrial solar spectrum. Remember, the table that we have worked on in the previous example, which is this table, it's fraction of black body radiation energy between 0 and lambda t for even fraction increments. So it's basically we are talking about a black body radiation as a reference. And we use that for the calculation of the emissivity. In this case here, what we're looking for is calculations of the absorptance for terrestrial solar spectrum. So we need a similar figure that can provide us with values or increments of delta F for terrestrial spectrum. And this table is found here. This is the one, table 261. It is available in the book in page number 63. And here it's making it a little bit easier for us, because this is the increments of the energy from 0 to 5%, 5 to 10%, 10 to 15%, up to 100%. And the corresponding wavelength, so it's not given as a wavelength into temperature, just the wavelength right away is given. So for this case, it depends on how many increments you need to do for this case. As you can see here, we selected to make it an increment of 0.1, from 0 to 0.1, from 0.1 to 0.2, from 0.2 to 0.3, and so on, up to from 0.9 to 1. And the corresponding value of lambda is given right away. So for example, if I need for this case to go from 0 to 0.1 as an increment, so I'm as if I'm taking each two of them as in one batch, like this. Why we are not taking it as is? Just to save time, which means that you could have done the same example, but taken every line. You don't have to combine lines. If we decide to combine the lines, so going from 0 to 10% or 0 to 0.1, the mid value is 5. So the corresponding value is this. So the first lambda you are going to take in your table is going to be this. And then from 10 to 20, the mid value is 15. So this is the value that you are going to take, which is basically, it's the value that's being repeated here. From 20 to 30, the mid value is 25. So, and so on. This is what you are going to do. So for this table, this is what we did. From 0 to 0.1, the mid value at 5. From 0 to 0.2, the mid value is 0.15, and so on. And you calculate the value of lambda. From the figure, you are going to go to each value of lambda and get the corresponding value of rho. So go into this figure again, and for each value of lambda, you are going to get the corresponding value of rho. Then you are going to sum all the values of rho that you calculated here, which sums up to 1.21. You are going to then use the definition of alpha as 1 minus 1.21 over 10. Then you can get the corresponding value of alpha for this case. This is a part of this of that the course that which is left for reading, general reading for you to get how to do the measurements for surface radiation properties. And another very important application in terms of the properties is what we call the selective surface. Our information that we have learned earlier that even what you studied in physics, that black bodies are absorbing all the energy falling into it, but it is emitting all the energy does it have. Shiny surfaces or white colors or light colors are receiving less radiation, but they are emitting less radiation. But it gives the impression that the amount of energy which is falling on a surface is basically either reflected all or absorbed all, which is not really the case. It depends on the temperature. For example, if you are talking about a solar collector, and the solar collector has an absorbing surface, this absorbing surface has been painted black. This means that it's going to absorb almost all the energy falling into it, which is true. But does it emit all the energy falling into it? This is the issue, because the properties of absorbance and emittance depend on the wavelength. And the wavelength is the reciprocal or equal or proportional reciprocal adversely proportional to the frequency. So short wavelength means high temperature. Long wavelength means low temperature. If we are able to control the properties of the surface in terms of high temperature and low temperature applications, or short wavelength and long wavelength applications, then we can do something which is useful for us. What do we need? We need the solar collector that can absorb all the energy falling into it and does not does not emit a big part of it. We need it to absorb the energy, the emissivity, we need it to be low, but the absorptivity, you need it to be high. Luckily, the range of temperature is different. What I mean by that is the following. When you are talking about a solar collector, it is exposed to the sun. So it is receiving energy from a source at a temperature of close to 6,000 Kelvin. But the surface itself gets heated to somewhere below 200 degrees centigrade. So when it emits the radiation, it emits radiation at a wavelength which is longer than the range it has received its radiation. Again, solar energy is at very high temperature, which means that we're talking about high frequency and short wavelength. So at short wavelength, the surface is receiving tremendous amount of energy. When it emits the radiation, it emits it at its corresponding temperature. And the corresponding temperature lies in the long wavelength radiation. If we are able to control the properties so that it can receive much energy and emit a minimum amount of energy, then we are talking about what we call a selective surface. The surface is selecting the range at which it receives much amount of energy and emits minimum amount of energy. So this is basically what we are looking for. And this is what you need in a solar collector. You need it to absorb the energy. You don't need it to emit the energy. You need this energy, which is absorbed, is to be utilized in heating water or heating air or heating oil, whatever the fluid that you want to heat. So solar collectors should have high absorbance for radiation coming from the sun. It is required to have the long wave emittance to be as low as possible. You don't need it to emit energy substantially to the surroundings. Otherwise, it will be losses. It will be energy lost because you need to make use of this energy in something useful, which is heating a fluid. So the temperature of most of the flat plate collector is less than 200 centigrade or Celsius, 473 Kelvin, while the effective surface temperature coming from the sun is about 6,000. Exactly, it's 5,777 Kelvin. So the wavelength is not the same. There is a little of overlap, but the overlap is not big. So short wavelength radiation coming from the sun, long wavelength radiation emitted from the surface. 98% of the extraterrestrial solar radiation is at wavelength less than 3 micrometer. Only less than 1% of the black body radiation from this low temperature is at this wavelength. The rest are at a wavelength which is higher, which means that we can maximize the amount of energy absorbed and minimize the amount of energy emitted, because we are talking about a different range of the wavelength with a slight overlap at a 3 micrometer wavelength. So we need to devise surfaces that have high solar absorbance and low long wave emittance. And this is what we refer to as selective surfaces. The concept is being shown here in this figure. Look at this figure. At a certain wavelength, the characteristic of the rho changes. Here, the value of rho is 0.1, which means that it has very high value of alpha. Alpha is 90, 0.9 or 90%. So 90% of the energy falling in this wavelength range is absorbed by the surface. So it is resulting in surface heating. But when it emits radiation at a long wavelength radiation, where the value of rho is 0.95, which means that the value of epsilon is 0.05. So it's emitting minimum amount of radiation. Yes, now we can determine the absorptance and reflectance based on the wavelength that we have. So if we know how the value of rho changes with the wavelength, then basically this is what we're looking for. The absorptance of solar radiation, designated as alpha, emittance is designated as epsilon, are calculated previously. We have the equations that we can calculate alpha and epsilon, and also we know how to get these values by knowing the value of rho, which is the reflectivity. There is another example here that we can consider before closing this issue, talking about for a surface shown in the figure, which is basically we are referring to this figure that you see in front of you, figure 481. So for this figure, calculate the absorptance of black body radiation from a source of 5,777 and calculate the emittance at a surface temperature of 150 and 500. So we need the absorptance to be calculated once for this temperature, and we need the emittance to be calculated for as if we're talking about two surfaces. One surface is 150, what's the value of the emittance? Another surface is at 500 centigrade. So let's see what's the emittance of this one as well. Now, the relation that we are going to do usually is this one. So absorptance for radiation from a black body at 5,777 is found by equation 464. So this is the equation we use, which is the incident radiation. And if you need the value of energy, then you can get the Planck's law to calculate the energy, which calculates the monochromatic emissive power as we have covered it earlier. So two values, alpha, are going to be needed. One of them is alpha S, which is the short wavelength range. The other one is alpha L, which is the long wavelength range. So alpha is equal to alpha S, short wavelength. The fraction through which the short wavelength is the one which is from 0 to lambda t. What is lambda here? It is the 0.3 that we're talking about. And the temperature is known to us. The long wavelength range here is alpha into the remainder. This is integration from 0 to lambda t. Well, the 1 minus f here is as if we're having an integration from lambda t to infinity. So it's two parts. Part of it is for the short wavelength radiation, part for the long wavelength radiation. F from 0 to lambda t is the fraction of the incident energy below critical wavelength. And the critical wavelength, as we agreed upon, it's a value of 3 micrometers. So 3 into the temperature of the sun, we're talking about the short wavelength case here, 3 into 5,777 is 17,331. Go to the table for 17,331, and then you can get the value of the absorptance as being calculated here. So 1 minus 0.1, where did we get the 0.1 from? It's actually from here. 0.1 is the reflectivity, so which means that the absorptance is 1 minus 0.1, which is given here, into this 0.979 is basically the value of F that we are getting from the table. Now for 17,000 331, the table, which is table 361, does not give me the 17,331. It has 17,000. The corresponding fraction is 0.776, and we have 18,000, and the fraction is 0.8907. So we can make like a linear interpolation to get this fraction here. So the fraction that you see here, the 979, is obtained from table 361A, and it is obtained by interpolation between these two values of lambda t. So lambda t is calculated for us here to be 17,331. In the table we have for 17,000 and we have for 18,000, and the corresponding fraction is given 0.9776, and the other is 0.9807. The value that we want is somewhere here, which is that 17,331. So 17,331 minus 17,000 divided by 18,000 minus 17,000 is equal to the value that we want, minus 0.977 divided by the difference between 0.9807 minus 0.977. This is linear interpolation, where you can get the corresponding value, which is this. Put this value here, substitute into the equation, and you'll see that alpha is equal to 0.88, which means that this surface is receiving 88% of the solar energy falling into it. I can repeat this part of the example again in the start of next class, and then we can continue to see the long wavelength value as well. I think I'll have to stop it here because of the quiz. What you need to do now is to log into Blackboard as usual, and the quiz is supposed to be released exactly at 9:15. So now when you log in there, you should be able to see it.
But Doctor, there is no file.
Then it should. Then it's not yet 9:15.
It is 9:15. I see quiz 2, but I don't see any file attached with it.
Did you check the assignments? Opening Blackboard as well.
There is a quiz
And
2, but there is no file inside the quiz 2 where we can see the question.
so assignment. Oh, the quiz is there, but you don't see the file.
Yes.
Check that. Yes. Can you refresh your screen? You should be able to see it now.
Yes, we can see it now.
Okay. Just to save your time, I have brought the information that you want in the second page. So in terms of either a table or graph, the relations are given here up the table, the value of the declination angle, delta, and the value of omega s, sunset hour as well is being given. I mean the formula, and you are going to solve only for one line corresponding to your ID number. Below the table, you can get the value of n based on the number of the days of the year. And the second page, you can find the ratio HD over H and the table that provides you with the value of H naught.
Doctor, so we don't need to calculate it's not
No, you don't. H naught, you can
by
get
the
it directly from the table. It's a long formula. That's why I thought that the table would be a better way to get it. An easier way, I mean.